Hello. Yes. All right. So that technical issue aside, everyone can hear me now, right? Here in class, everyone can hear me. Okay. All right. Let me start the. Okay. All right, everyone. 6 minutes late, but all right. Welcome to Geometry of Data. Today, so what we'll do is we'll continue from what we were discussing last time and flow-based models, and then we'll discuss self-supervised learning today. Before we do unsupervised learning, so there's a change in the schedule a little bit. We'll do self-supervised before we do unsupervised because of time crunch and we're sort of moving some topics around. And we want to spend a little bit more time on self-supervised learning because it's newer and there's more applications that you will find even in your project and general in the latest trends of machine learning. There's more applications of self-supervised learning. So let's just look at that first. So before we get there, we were sort of discussing the affine transformations and what different flow-based models are and what were the ideas that were working. So the idea that we had discussed, which was idea number 2, that was sort of almost there, was working, was you have a system like this where you have, let's say, a layer which is built up of half the input. So the first half of x1 and x2. So what you do is that you split the input into 2 parts, and then you just copy the top half of this embedding as an identity map into the output directly. And the bottom half is what you sort of transform, and you apply affine transformations here to get this output Z1 and Z2, right? And what this ensures is that the Jacobian of this transformation is easy to compute and that you can sort of optimize it using like gradient-based methods. So this is what is called as an affine coupling there. This terminology, I don't think you if you see this in some paper, you know what this is. Just an affine transformation where half of the input is just being copied as it is, right? And we had seen that the Jacobian of this type of transformation looks like this, where this is just identity, this is 0, this is d z2 by dx1, and this is the diagonal elements of S theta, right? And what is happening here is because we only want the determinant of this matrix, because this is the term that we don't know is getting multiplied with 0. What we have is just the diagonal of this matrix that we want, and that is sort of easier to compute. And just to sort of make this complete, the transformation that is happening here is that Z1 is just equal to X1, the identity map, and the Z2 is just a affine transformation, which means that it's S theta times element wise X2 plus like a bias term. And note that this S theta and D theta are both sort of predicted using X1. So this also is using sort of X1 as the input, which is why this doesn't disappear. Because DZ1 will depend on DZ2, sorry, DZ2 is still dependent on X1 because these values are sort of dependent on X1, which is why this part of the matrix doesn't go away. But because we are multiplying it with 0, it doesn't really matter, right? So, all right, so this is what was the idea that was sort of working in flow-based models. And there is one more sort of modification to this, which sort of generalizes this to be more expressive and be able to sort of capture the real distribution a little bit better and be able to model real world complex relationships between image data and text data and things like that. Because here also the thing is that this is working as one layer, but the problem is that the expressive, like how expressive this model is still very limited because half the input is just getting copied, right? So it's not really too expressive in the sense that it is not able to capture like very meaningful relationships because half the input is just getting copied to the output. So the distribution that you're sort of modeling, half of it is just a Gaussian distribution. So it's not really too powerful to be able to sort of actually sort of model real world data. So to extend this to like actually being useful, let's look at how we compose a bunch of these transformations together to design like a network that would be expressive enough. Okay, so let's just assume that this transformation, this one layer is called F1. So F is just an affine transformation layer. Okay, so what we are looking at here is camera. We have to compose transformation. Okay, so we design an overall function f, which is just a composition of individual functions f1 composed with f2 composed with f3 composed with f4. Right, so this is k. So let's say you have k layers of these affine transformations, and overall together it's just one function f, right? It's just a composition of multiple affine transformation layers. So what we want is that each of these should be individually be following the rules that we have sort of set for flow-based models, right? Everything that we have discussed here should be applicable to each of those functions independently also, right? So that would ensure that if you have an input x, you can apply f1 to it to get h1, and then you can apply f2 to this to get h2, and so on. Finally, get hk. And because these are flow-based models, and what we want is that all of these are independently invertible, which is what we want from a flow-based transformation, is that each of these should be independently invertible. So in that case, what would happen is that you would have functions which are inverses of this also, well defined. So f1 inverse should be defined, f2 inverse should be defined, inverse should be defined. Right? So this means that if you have real data here, you are able to use a composition of such transformations which are independently flow-based to sort of design an invertible pipeline that takes the real data and embeds it as an embedding HK, and then is able to recover it through sort of inverting each of these transformations independently. Another thing that we sort of should note is that because we want to sort of optimize this using gradient descent, it is important that when we calculate the gradient of the entire model, the gradients independently should be sort of composable together also. Like the backward flow of the gradient should not break because of any of these transformations being composed together, right? So what happens here is that we know that the gradient of a composition of two functions, which is, let's say, f2 composed with f1 of x, is just the independent gradients of by chain rule of f1 of x times, right? And because this property holds, this composed like layers by layer attachment of normalizing flows is overall differentiable completely. And because all of this is invertible, you can use it as a flow-based model where it is embedding data as like a latent vector, and then is able to recover that data from that latent vector, right? So, and here also like one more thing, because of this, for the sake of completeness, the determinant of individual Jacobians J1 and J2. I'm just assuming that there are only two layers in this. So the determinant that we will need to calculate of the overall model will be the multiplication of both the Jacobians because they are applied in series. And then we have to get the determinant of J1 and J2, which would just be equal to the determinant of J1 times the determinant of J2. And note that because each of these are individually affine transformation layers, we know how to calculate J1, determinant of J1 very easily using the math like that. So each of these independently is equally easy to calculate. So you can just sort of compute them together like this, right? So now we saw what an affine coupling layer is, right? So this, you can understand the intuition of how this is working. This is working because we are copying half the input, and that sort of lets you design a Jacobian matrix, which is easy to compute, right? This is why this whole system works, because every transformation layer has a very easy to compute Jacobian, right? But this type of transformation, which is just direct copying of half the input, is not very powerful. You can come up with different types of transformations like this, which are slightly more powerful and work better with image data and other types of data, and still hold, like this property still holds, like the Jacobian is still easy to calculate because you're still sort of copying some data from the input, but you're not doing it as naively as in this case, right? So I'll tell you a couple examples of different types of such transformation layers which can be used in flow-based model. Okay, so this paper called Real NVP sort of introduced two types of layers. There's this one checkerboard based copying, where what happens is that instead of copying half of the input, you copy like half the input in a checkerboard pattern. Like you, let's say the image is like W cross H. You split this image into like equal portions, and then in the transformation you copy half of these cells directly to the output, whereas the other half is transformed, right? So instead of copying half the input like this, you sort of copy half the image like in a checkerboard pattern, and the rest of the image, which is not sort of copied, is transformed using an affine transformation like this. Okay, so the checkerboard pattern sort of ensures that you are sort of copying information from all across the image, and because this, in this pattern, the model is better able to fill in the holes because it has information around it because of this interleaving of the information that is going through this transformation. It's easier to model image related relationships through a pattern like this. Okay. There is another method also which is called channel partitioning, where if the model has, let's say, a feature map like this, which is width cross height cross, let's say, some depth C, what you do is that you sort of copy half the channels from this, just randomly select the alternate channel and only copy that much, so that the output is now the first half of the channel C by 2 are exactly copied from the input, right? Instead of copying data in a checkerboard pattern or just like the first half, you copy like alternate channels. So half the channels in the transformation are exactly copied, and the other half are transformed like that, right? So you copy C by 2 channels just exactly, and the other C by 2 get transformed, right? So you get H plus this is C by 2, and then you concatenate these together, and that is the output of this. Okay, that makes sense. So because this is sort of working at the channel level, it's still sort of getting some information which is able to sort of capture higher or more complex features rather than just copying the first half and using the second half as transform. All right, And there was this paper called Globe, which came after this, which also sort of introduced some of their own tricks over this method, where they introduced 1x1 convolutions, and they found that 1x1 convolutions are easy to invert. So they have their own tricks of being able to do exactly this and design like a powerful flow-based model. And yeah, and Glow is the latest one. So if you want to like read a little bit more in detail about flow-based models, this is the one that sort of works now. Real MVP was the precursor to this, which has like a lot of fundamentals of how these models are designed, but this is the one which finally started working. All right, so let's now finally go to self-supervised learning and see what that is all about. Also, like if somebody is sort of taking notes and I start erasing, please feel free to stop me, because I don't have a sense of when, what part of the board is copied already. So let me know, because we don't have any slides. That's all you have. So ask me to stop if you want to write something down. All right. So self-supervised learning is a new paradigm of machine learning that has become very popular in the last 3 to 4 years, right? And this, essentially, if you think about it, it is a form of training deep learning models without having annotations, right? But that is the exact definition of what you consider unsupervised learning as well. So it's not something very different from unsupervised learning. It's just a paradigm which is new in terms of how it is defined and how the problem is structured itself, that you call it a different name. But essentially, it's just being able to train deep learning models without having to annotate a bunch of data, right? So, and because the techniques that were sort of introduced in this round of unsupervised learning were so innovative and so different from what we have been doing before, that this whole field itself got a new name. Okay, so in the last 3-4 years, what has happened is that the amount of data has increased tremendously, and you have like really large data sets that are available to train for both images and text, and also cross-modal data sets. But the amount of annotation with this data has not really increased in an equal proportion. So what we want to do is we want to be able to learn without having annotations and learn some intrinsic structure in the data before we sort of try to train a model for a specific task. You want to do some general training so that the model sort of already understands what images looks like, what text documents look like, before you sort of fine tune it for a specific task to classify images or classify a document, right? So these days, all deep learning models are always designed in 2 stages, and we'll sort of look at these 2 stages and see how self-supervised learning fits in, and at what stage do we need like a new paradigm for training such models. Okay, so the first step that all models usually take these days is a pre-training step, right? And this step is characterized by training on very large scale data sets. And large scale is like really a keyword here. And by large scale, I mean like even ImageNet dataset, which has like millions of images, is not large enough for the models of the day to train the billions of parameters that they have in the model. So like large scale means like really large scale. And the aim of the step is to sort of learn some intrinsic structure in the data, right? So you are not really focused on sort of solving a task, like you don't have a task of image classification or maybe like tumor detection or any specific task that you want to do just yet. What you want to do is that you want to learn just an a very exhaustive intrinsic representation that sort of already learns the structure of the data. Like it understands what circles are, understands what different types of patterns are, and already sort of has a sense of what real images look like or real text looks like. To learn some intrinsic structure. Right. And then the second step is the adaptation step. Right. And here what we do is that we take a model which has already been trained on a large data set. So it already has like a sense of what the data looks like and has learned some intrinsic structure. Then you sort of fine tune. Fine tune is one type of adoption, but then you sort of adapt this model to downstream tasks using labeled data sets. So you train on a downstream task. Using a labeled data set, right? So you use a small data set, and this data set can be like really small. You can have like 10,000 examples, 5,000 examples, anything that is not comparable to the large scale data set. You can sort of already use the information that was learned in the first step and then try to solve a smaller problem, which is like a subset of the problem that you were trying to sort of learn in the first step, right? So here, this step is more task specific. So you're not really learning anything intrinsic, and you just wanted to solve like one task. Okay. Right. So these are the two steps that we'll sort of base our discussion around and sort of try to understand where different types of machine learning or different types of AI-based paradigms fit in this type of a structure. All right. Any questions so far? No? All right. Okay, so let's look at the pre-training step a little bit more in detail. Okay, so let's say we have a large data set as such, which sort of has a bunch of examples, x1 to xn. And note that we don't have any corresponding labels. We don't know what these data points are. We just have like a set of a large number of data samples. What we want to do is that we want to learn a model f theta, which takes in x and sort of gives you f theta of x, which is known as the representation of that data sample. You would see that this is also called the embedding or features or any of those terms. So what you do is that given a model f theta, what we want to be able to do is that we embed the input sample x as a representation which is smaller than the size of the data, right? So maybe it's 10 dimensional. Okay. And how do we do this? Is that you sort of optimize over a loss. And I will not like there are different types of losses that you can use to do this type of pre-training, and we will look at a couple contrastive losses a little bit later, like in a few minutes. But what you have to generally do is just optimize a loss function. So I'll just write the general optimization principle, and then we look at different types of losses that can be used at this step and different losses that can be used at the adaptation step. All right, so for the pre-training, the loss is called L pre-training. What we have is that we're trying to optimize these parameters theta. The loss is just a summation over the entire data set equal to 1 to n, a composition of this pre-training loss theta. Right. So we're just trying to optimize these parameters theta over the entire data set using this loss LK. Okay. Yeah, and once you optimize this, what you get is that to get theta hat, which we sort of call the trained parameters. So these are the trained parameters of the model. And once you train the model, you get like the optimal parameters theta hat, which then can be used to sort of embed this, right? So this is very general, and this is what happens at the pre-training step, right? So you are able to already get a pre-trained model, which optimizes on a loss like this, and this can be like any loss, and we'll see what kinds of losses we can use here. But yeah, but you take the data and you sort of try to minimize any loss to get a pre-trained model which already has some understanding of what the data is, right? And then the second step is then the fine-tuning step, or the pre-training or the adoption step. And this, you recall, if you recall, is dependent on the task. So the data here is with labels, right? So you would have x t. By t, I mean that this belongs to some task. And you have like a small data set like this where you have x t comma y t paired. And you have, let's say, x t n t also samples. Right? So you have NT samples on which you want to train a model, and this is task specific. So, for example, if you pre-train the model on just images, the model will start understanding what images look like and what kind of structures it expects in an image. But then you fine tune on, like, let's say, for example, identifying dogs or something like that. So you can just get like 10 images or 20 images of dogs. So now the model already has seen a large number of images and understands what kind of real world images it expects. You can sort of train it on a specific task. Even if the data set is much smaller, the model will be able to sort of identify the differences and solve that task for you. So this is a task specific data set that you want. And if NT is equal to 0, this is known as zero shot learning. And by zero shot learning, it means that without having any extra samples for a given task, the model is already able to generalize to a new task, right? So you really need no samples for that given task for the model to generalize to that task. So if you can train a model like that, which is already general and already is able to perform a bunch of tasks zero shot without having seen any examples of that task, you call it a zero shot learning problem. Okay. And if say NT is small, as in less than about, let's say, 50. I mean, even smaller than that, but this is a moving scale. As the papers come out, like this keeps getting smaller and smaller. But if you have like a smaller number of samples like that, this is called future learning. Right? But how do we do this adoption step is also like a thing that we should discuss. So one thing that is common and people do is that you train a pre-trained model and then you only do a linear probe on that model to fine tune it for a specific task. Like, so what does that mean, right? So we want to see what a linear looks like. Okay, so for a given image X, what we have already from that model is that we are able to sort of embed it as a representation like this, right? F theta hat of X, which is the trained model, and we already are able to embed this image as a representation, which is sort of a representative of the information that is contained in that image. Okay, what we do is that we just transform this using a linear matrix W transpose and multiply it, and we assume that this is the prediction of the model for a given task. Okay, we just learn a matrix W, we transpose it, multiply it to the representation that we had there, and this linear transformation gives you the prediction from the model. Okay, that makes sense? Because if, let's say, this is m-dimensional, you can also use an m-dimensional vector to just compose it into one value, and that would be the probability of whatever task you're trying to solve. So for example, this is just the embedding of image of a dog. You only need to tune this matrix to sort of transform that embedding into giving you a prediction value, which should be between 0 and 1, and should tell you what is the probability that this image is a dog. Okay, and you have a different weight matrix for different tasks. So a dog identification task would have a different weight matrix, and a cat identification task would have a different weight matrix. So depending on what task you're defining, this linear probe will change. And if you have a task which instead of giving you just one probability of one object, if you want like a probabilities of two objects, let's say you want to train a model which is just between cats and dogs. So it gives you of an image of being, gives you the probability of an image containing a cat, as well as gives you the probability of that same image containing a dog. In that case, this weight matrix would be m times 2, in which case you will convert this representation into two values. The first value will be the probability of it being a dog, and the second one of it being a cat, right? So depending on what the weight matrix is, you can define multiple tasks that can directly work on the learned representation that you do during the pre-training step. Okay, but now there's another problem, is how do we learn this W, right? This W is not learned, this is already trained, and we already freeze these parameters theta hat during pre-training, but we still don't know what this W is for different tasks, right? So how do we do that? So what you have to do, learning okay, so to do that, it's nothing complicated. So now we know what the prediction looks like, and we also know what the prediction should be, because recall that at this step we have some labeled data as well, right? So because we are trying to fine tune or adopt this model to a specific task, we have some labeled data set for that task. So you can directly just minimize a loss for the parameters W on the smaller data set, which goes from I equal to 1 to NT, which is this task data set, and sort of optimize a loss L task. And this L task could be anything depending on what kind of task it is. You can sort of see that this could be a binary cross entropy or any type of loss that sort of compares the output to the label. And this is the ith label. And this is the ith sample, right? Right. Right. You take samples from here and you optimize the W on a loss over this data set. Okay. Make sense? Now, another way of doing the same thing is, and note that here this is frozen, right? Which is why the optimization is not over theta, because theta is kept completely frozen. But if you want to see what happens when you sort of slightly modify theta as well, that is called fine tuning a model. So you have a model that is already pre-trained on a larger task or a general contrastive loss, which generally understand what images and text sort of represent. Then you try to fine tune that on a specific task. What you do is that instead of just freezing theta hat, you also optimize over theta hat and W both. So when you optimize both of this in the same type of setup, then it's called a fine tuning step, right? So the adoption in that step, in that case, is happening via fine tuning. Okay. Now let's go back to the pre-training steps so that we can see a couple methods of doing such kind of pre-training without having labeled data. Okay, so very quickly, let's look at supervised pre-training because it's just the first step of how we sort of learn about machine learning, deep learning, and how these models sort of perform with labeled data. So let's just look at supervised pre-training and then we can look at self-supervised pre-training. So in supervised, what we want to do is that we want to learn neural network of the form U transpose F theta of X. I'm writing it as such for a specific purpose, and we'll see what that is. Here, the UT is just the last layer of the model. So any model that you sort of define, if you just sort of write the last layer as this UT transformation, which is just the last linear layer that is making the final prediction. Because it's a supervised task, this UT will have a specific task-based structure. Like, for example, as we discussed for WT here, this is the last step is always dependent on what the task is, because the output will have the same number of probability values as the number of classes in your task. So, for example, if you're training this for a supervised, like if you're doing a supervised pre-training step on the ImageNet dataset, this UT will only give you like 1000 different values, 1000 different probability values for each class in the ImageNet dataset. Okay, so which is why I'm writing the last layer separately, and this is the rest of the model. So any model, if you just remove the last layer, the rest of the model is just F theta X. So now you train this type of a model with a labeled dataset using any kind of a loss that depends on what the task is, what the dataset is. If you are doing like, let's say a classification task, like for example, just an ImageNet pre-training, what you would train it on like a cross entropy type loss, and that would give you a model like this. And then what you do is that you throw away UT. So you just discard the last layer, which is U, and that gives you a pre-trained model. That's theta. Okay, and then you can use this as a pre-trained model in the adaptation step to sort of specifically sort of train it on a fine-tuned, a fine-grained task. Right, this is just supervised pre-training. Any questions so far, like about anything? Because all of this has been very general, like there's not a lot of math, it's just trying to give you some intuition of what's, how things are set up. So yeah.
How is the loss pre-train calculated? Because usually how loss is calculated is like you have an embedding, you have a prediction, and based on that you calculate the loss. But in pre-training we don't have a prediction value. So how?
Exactly. So we'll just do that right now. Okay. After this, this is now going into the territory of, we said that we want to sort of optimize this pre-training loss, but we don't know what this loss is because there's no labels in the data yet. So we want to sort of come up with a structure which can already sort of start learning some structure without having and additional information about each image of what that image is, right? So we need to sort of exploit some inherent structure in the data to be able to learn something from it without having any additional labels, right? So how do we do that is what we will tackle in self-supervised learning. Okay, so we saw supervised learning, so now let's look at contrastive learning. And contrastive learning is the most popular self-supervised learning method, right? So I'm writing that contrastive learning is the most popular self-supervised learning method these days. And yeah, let's look at how it works. So before we look at what the loss is and how we sort of structure it, we need to sort of understand what data augmentations are. Okay, so let's quickly see what we mean by data augmentation. So data augmentation is just a technique to transform an image or any kind of data, which in such a way that it sort of still retains the same information, but it does not really exactly look at the data point as it did before. Okay, so for example, let's say we discuss all of this for the image case first, and then we look at one case where we look at it for text as well. So far, like right now, we're discussing for images. So let's say you have an original image like this. There are different types of augmentation that you can perform on this. The first one is, let's say, is random crop, right? Which is nothing but just getting a random part of the image as your data, right? So you just take the image and you get a random crop out of it. That's one type of augmentation that you can perform on an image. Okay. Another type is flip, where you just rotate the image, right? So it's a dog, then it's like a sideways dog. So that's one type of a data augmentation that you can perform. Then there are color-based transformations, where what you do is that you take the image and you sort of modify the color, the gradients, the contrast, and just the physical attributes or the brightness of the image to sort of make it look slightly different. So composing all of these transformations together, you can come up with different views of the same data point, right? Having the same data point, if you apply all of these transformations randomly, like each of those randomly, so you can have like a random crop which is flipped but also color transformed, a random crop which is a different area but is not flipped. So you can create like various views of the same data point, right? So that's what data augmentation does, is that you give one data and it sort of generates different views of the same data point with the same information, but in different formats. Okay. So what do we want from our model? So now that we don't have any labels, what is the basic thing that we know about the data? Anything that we sort of can sort of leverage to make the model understand or try to train on, being able to distinguish samples or understand what images, what kind of structures are in images. So is there anything intrinsic that you can come up with that is present in every data set, irrespective whether it has labels or not? I mean, just something intrinsic about data itself. Any guesses? Just, anything is fine. Like, for example, you have a bunch of images, right? But we don't have any labels. Like, we don't know which image is what. You can't have someone look at the images and be like, that these two images are at least belong to the same, category. Like, you can't even do that. So what do we know still about this data set? So the only thing that we can surely say is that no two images in the dataset will have the same information, right? Like if you truly look at what an image sort of represents, only the augmentations of that image will have exactly the same information, right? You can assume that if there is an original image which is of that specific zebra, if you apply different transformations, you can make the assumption that any transformation that you apply will still sort of have the same information content in the image as the original image. Any other image does not classify as a positive pair for this image other than anything that is augmented from this original image. Okay, so that is the basic inherent thing that we know about any dataset, is that no two images will have the exact same information in them, right? Any two images that you pick, if they are randomly picked and are not the same image, are not the same data point, should be embedded far apart. Whereas any two images that sort of belong to the same information category, or for example, are coming from the same original image, should be embedded together in your latent space, right? So that is what we want. We want an image, let's say we have a data point X, and we apply augmentation 1 on this augmentation A on this to get XA. And we also apply another augmentation B on the to get XP. Right? We want that we want F theta of XA and F theta of XP to be close. Right? That makes sense. What we want is that the embeddings of the augmentations of the same data point should be close to each other. That's it. But now, if you sort of think about this, if this is the only thing that we want, then your model can sort of embed everything to the same point, okay? Because then everything will be the same. So in that case, this will be satisfied. Like this is the extreme case of that condition being satisfied. And so any kind of optimization problem, which is only trying to optimize on this, will not work, because it will always be the best solution to embed everything as the same thing, right? Just identify, just create like an L map, and whatever the input is, just keep predicting the same value, and this would be completely satisfied. But that is not what we want, because it's a user's model, because it's embedding everything in the same thing. So to counterbalance this, we also add another thing that we want from this type of optimization that would help us actually optimize this model. So as a counterbalance, what we want is that for two random examples, which are not the same example, let's say X, we apply a transformation to this, and you get XA. And you have another sample Y, which is a different sample, and you apply some augmentation to this, and you get YA. I'm denoting this by YA because it does not matter even if the augmentations on the other image is the same, right? It's still a different image. Like it still sort of has different information, even if the augmentation on this one is the same. So this could be A, B, C, D, anything, but it doesn't matter. It just is a different image. Okay. So here, yeah, so one more terminology that you should remember is that XA, XB is called a positive pair. And XA, YA here is called a random pair. It's also called a negative pair, but the term negative pair is not entirely accurate, because there is no guarantee that these two belong to different classes. Like these could just be images of dogs, but just different dogs, right? So there is no way of saying that these two are negative in any sense. Like negative in the sense like they might belong to the same class, they might be the same scene even, but they're just not the same image. So it's a random pair that way. Okay. And to counterbalance this requirement, the second requirement is that we make f theta of xa and f theta of xb, oh sorry, y, right, as far as, right? So now we have two requirements that we want to fulfill. The first thing is that the same data point, even if it's augmented differently, should be embedded as the same embedding, right? This is the first requirement. And the second requirement is that if the data points are different, irrespective of what the augmentations on those data points are, those two should be embedded far apart, right? So now we have like a balancing act where we want this as well as this, and the optimization problem that comes from this will give you a model that is able to do both the best, right? Okay, so how do we do that? So now we finally looked at this paper called Sinclair, which is just a simple framework for contrastive learning, right? So this is the simplest contrastive learning algorithm, and this the objective that is proposed in this is so powerful that all contrastive methods after this, even between different modalities, are just different variations of this objective function. Okay, so once you understand what contrastive loss here is, it's just very simple to extend it to anything else. Okay, so for Sinclair, let's see how that problem is set up. So you take a batch of examples. Take a batch of samples, right? Which means that you have x1 up to b, right? And then what you do is that you create augmentations. Okay, and we specifically create two augmentations, and we'll see why. Because we want like positive pairs and negative pairs as well. So for positive, so for the first augmentation, you have xa1 dot 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 to xa capital B. And for the second set of augmentations, you have xb1 to xb. Okay. So now what we want is that a positive pair from here, which means any two samples which belong to the same data point, should be embedded closer, and any other data point like this one with any other point should be further away. Okay. So the overall, so let's look at the contrastive loss function first, and then we can sort of look at each term of that loss function and see how, sort of it's enforcing these two criteria. So the loss is this. Yeah, so this is the overall loss function. It looks a little, complicated, but it's very, it's as simple as it can be. So in the numerator, you'll see that this term A is there. The same term is there in the denominator as well. This is here, and this is a different term, right? B. So just by looking at this, like for basic, just by basic arithmetic, you can say that this overall term is increasing in B. Like for example, if the loss goes up, this means that B is also going up, right? And if the loss is going down, this means that A is going up, right? And then let's look at what A is, right? So A is just an inner product between the representation of the first augmentation of a data point and the second augmentation of the data point. Okay, so if these two are close together, this inner product would be higher, right? That makes sense, because if these two are just the same vectors, for example, this would be highest possible, because just an inner product between the two representations. So what we want is that the higher this value is, the closer these two are to each other, because it's just and product between this representation and that representation. And that is what we wanted, is that the representation should be closer together. And when the loss is going down, this value is going up, which means that the representations are getting closer and closer together as the loss is going down, which is what we want in the first criteria. That makes sense? The second criteria is that this value, you can see that when I is not equal to j, which means that for every pair of negative samples in your batch, like if you have a batch where there are B plus B, like there are B different samples, and if you're comparing each of those samples with every other sample in the batch, the diagonal element of this would be all the positive pairs, right? Because it's the same. And all of the non-diagonal elements will be the negative pairs. So this summation is over all of these non-diagonal elements. So for all of those non-diagonal elements, the agreement between the dot, like the dot product between the representation of negative pairs should be minimized, right? Which means that as the loss goes down, this value keeps going down as well, right? Which means that the agreement between samples that are not paired are is decreasing as the loss keeps getting better. So both of those criteria are sort of satisfied with this objective function, and this is essentially how you sort of train these models. And this loss function is called the InfoNCE loss function, and it came from an information theory perspective of how to optimize lower bounds on mutual information. And we can we'll look at that a little bit more when we learn a little bit of information theory, and you'll see how different bounds give you different objective functions. And this bound comes from a specific Donskill-Verdun lower bound on mutual information. There is an InfoNC based lower bound on mutual information as well, which gives you this objective function that you can then finally optimize training model like this. And the lower bound by lower bound on mutual information I mean is that what you're trying to do is that you're trying to maximize the mutual information between different views of the same data point. Like even if you have two different augmentations of the same image, the mutual information between these two augmentations should be maximized. And to maximize that mutual information, this is the lower bound that you use to optimize the overall. And we'll look at that from a mutual information perspective as well in some later classes. All right. So this is all in the context of image-based models. We'll very quickly look at language models as well, so that you get a sense of how self-supervised learning works in that scenario. Is this loss function? Can I use it? Okay. So Okay, so for language models, the data that we have, let's say, is of this format. You have x1, which is a token, dot dot dot, up to x capital T, right? And let's say that each token here is just a word. So you have like a large amount of text, which is just like concatenated together in just one string. So let's say you have like one Wikipedia page, and the entire Wikipedia page is what you want to train a model on. And people do this with like billions of Wikipedia pages. So like multiple trillions of words, just sort of flowing together, and you sort of try to train a model so that that starts understanding language just by sort of reading a lot of language. Okay, so but we sort of work at the granularity of a word. You can also work like at the granularity of a character, where instead of x1 being one word, x1 can be one character as well. But that becomes like a very complex problem to solve, because then it's very hard to sort of understand, like learn the relationship between the characters as well, of how they form words, and then how words form sentences becomes a more complicated problem than we need to solve. So this works at the granularity of tokens, and these tokens usually are one word or sometimes even smaller than one word. So for example, ing is a different token than do. Like if you are to write doing, it will be split into two tokens, which is do and ing, right? So things like that happen. So these are similar to words, but sometimes less than a word even. So what is a language model? What do we want from a language model? So a language model should be a probabilistic model which models this distribution, the joint distribution of all of these data points together, right? Yeah, but this is like very hard to model. Let's just apply chain rule to this, okay? So when we apply chain rule, what you get is that this same thing can be written as P of x1 times P of x2 given x1 times P of x3 given x2 comma x1 times dot P of xt given one right? Just a chain rule on the probabilities. And so here, if you get like the probability of an intermediate word, x small t, that would look like this, right? P of xt given everything with t, t minus 1, t minus 2, right? And this is a conditional model that we would like to learn. So if you look at this closely, what is this doing? This is just predicting the tth word by just looking at every word that comes before it. So if you have like a bunch of text, if you give it all the text before this word comes, it should be able to sort of predict what the next word is. So given a sentence, if you give it the first four words, the model should be able to predict what the fifth word is just by looking at the previous words, right? So that is the kind of conditional probabilistic model that we want to train, because just training like a joint probability distribution model is so difficult that we sort of chain it, sort of split it into different conditional probability and learn these conditional probabilities separately, and that would give you like some sense of conditional probabilistic model which you can sample from and complete text and perform different tasks. Okay, so let's just see how this is done. Like the latest architectures that are used to do this are transformers. So let's just very quickly see how that works. Okay, so step one that we want to do is that for each word in our vocabulary, we want an embedding here, right? Which is a d-dimensional embedding. And this just means that every word, sort of should be represented as like a as like embedding. So like just the word should be should be able to convert that word into like 1D representation. Okay. So just being able to do that is what we want as the first step. Like that for each word in the vocabulary, you should be able to convert that word into like a representation. Okay. And then what we have is that imagine that you have a transformer, and very quickly a transformer is like a neural network architecture which takes in a sequence and gives you a sequence. So if you have like, let's say, n tokens that go into a transformer model, you can sort of extract n tokens which are all sort of just transformations of the same token. So you have, let's say, the first word ex1, like x1 is the first word, right? So you convert it to ex1, which is the embedding of that word. You give that to the transformer, and that gives you the C2, which is what we will use to predict the probability of the second word in your sentence, right? Because it's taking in the first word, predicting the second word. Okay. This ex2, C3, and so on, right? So that is how you sort of model these sentences, that the first one goes in and you predict the second word, then the first and the second word go in, you predict the third word, and just like that, you are able to sort of model the distribution. And so overall, what you do is that you use CP to predict P of xt given x1, x2, to xt minus 1, right? And if there is a model, if there's a transformer model which is only taking into account the previous tokens for predicting the next token, it's called an autoregressive transformer. Any transformer that is only looking at the sequence behind it to predict the next word or the next token in that sequence is called an autoregressive transformer or an autoregressive model, because it's automatically regressing over its own output, right? And this also is not just one value, because this sort of needs to be what the probability of this word xt is over the entire vocabulary, right? So for every word in your vocabulary, you should get a probability value of how likely that word is at this location xt. Okay, so instead of this being just one value, this will be a v-dimensional vector, where v is the vocabulary, size of the vocabulary, right? Yeah, v is the size of the vocabulary. I was not writing that. And each column, sorry, each row is just the probability of that word xt being equal to the first word of the vocabulary, right? Given everything, x1, xt minus 1, and so on. And this is the xt being equal to v, whatever the size of your vocabulary is. Let's say small v is the size of the vocabulary, so v given x1, right? So this is the vector that we are trying to model. All right. So similarly, like, I mean, now that you are able to sort of predict CT, what you can then do is that you can use the representation of CT as the entire representation of the sentence that comes before it. Okay. So let's say you want to do a sentence classification task. You want to give a model a sentence, and the model should be able to predict if that sentence is a positive sentiment or a negative sentiment. So instead of giving the representation of each word in that sentence, what you can do is that you can directly give the representation of the last word, because that already embeds everything that comes before it, and just the last word's representation can then be used to sort of predict the overall sentiment of the sentence. So the whole document can be then represented as just one embedding instead of just a composition of all the embeddings or all the words in that sentence, right? Yeah, and just one more small thing is that with large language models, you also have this one very special feature is that you can sort of define any task as a language-based task, because language is the modality that we sort of communicate our ideas in intrinsically. So what happens is that if there is a task, let's say you have a science question based model that you want it to know some physics principles, right? So what you can do is that instead of sort of training a specific model that does that, you can train a large language model on a large scientific data set, and then you can come up with a sentence like you want to find out what the speed of light is. So you can say the speed of light is, and then ask the model to predict the next token, right? So the model will then look into its, whatever probability distribution, and based on what the sentence is, will predict something. It may or may not be correct, of course, but that is what the model can do just by training on large language, because you can then sort of define any kind of task in language tokens, because that's how we define tasks ourselves. All right. Okay. So thank you. We'll stop here. Next class we'll do a little bit of unsupervised learning. Also, we'll look at one more contrastive learning method, which is hyperbolic embeddings. Yeah, because that is something that you'll find interesting, because in this contrastive learning that we saw in Sinclair, everything is getting embedded to a sphere. But we will have another contrastive method where instead of embedding on a sphere, you are embedding on a hyperbolic sphere. All right. Thank you.
这节课
然后我听不懂呢。
啊，这节课纯华语课，
这么低。
很慢，也不见了，是
哦，
今晚就是今晚不是有什么活动啊？有了，有了，
是吗？
是的，
说有吃，好像是有吃的吧？
是今天吗？是今天吗？
那是的。
5点到几点？